1. Introduction of what electrons are. Why they flow through conductors and not insulators. Why do electrons flow from negative to positive? And also, why is 1 coulomb of charge 6240, and then there's just 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, a unit. Why is it that many? Hello guys, welcome to my first electronics tutorial. Today we will be learning the basics of the following topics: voltage, amperage, electrons and how many are in 1 coulomb of charge, Kirchhoff's laws and Ohm laws, and basic circuits like a battery connected to a light bulb. This will be the first video in a series. I don't know how long I will branch it off and revise it, but I'm going to try to make other uploads. Maybe, if I want to. Okay, so what is electricity? Electricity is the movement of electrons through a wire. Okay, you say, what is an electron? An electron is a negatively charged particle, like a positively charged proton or a neutral neutron in an atom. An atom is, an atom. Like I'm made of atoms, you're made of atoms, steel is made of atoms, glass is made of atoms. You can't touch and see the atoms, but the electrons do jump and stick from one atom to another atom. They flow in mass through the wires, so it's not just like one electron in a circuit just going around. It's a sea of electrons. It's trillions, quadrillions, I can't even talk, but I'm not going to re-record that. Unfathomable amounts of electrons flow through in even the most small circuits in just a second. It is important to note that the electrons can also flow through things that aren't considered a conductor. Like they will flow through air, right? But they don't want to flow through air. Not to say that they have really a choice. They will if they can, they'll shock you. But they'd rather flow through wires. So only a couple of the electrons will stray away if you have a good wire with a good insulator around it. But if you don't use a good insulator, then you might have more electrons that stray, or you might actually become a conductive path, or maybe some water or something, So don't get too close to the high voltage. Speaking of voltage, what is voltage, and how does it compare to pressure like pounds of force, like carrying a 20-pound dumbbell? What is current as well? And how is it the flow of electrons? Like water can flow and I can have water current, but how can imaginary particles be flowing through wires? Like I couldn't even imagine that. I couldn't imagine imaginary particles flowing, but I could imagine water flowing, or perhaps air flowing through a system. Like fluid systems are pretty close to electrical ones. For instance, your bike tires, you can pump them up with air current. The air flows into the bike tire, and then you pump your bike tire, let's say up to 60 pounds per square inch. That's a unit of pressure that your bike tire is at. It's how many pounds of the square inch, and pounds is a unit of pressure. Just how how many volts you have is a unit of how much electrical pressure you have. This can also be called, like some other people call it, electromagnetic force or potential difference. I kind of like, but it doesn't really matter how you say it. It's just pressure, really. And this I like to think of as the cause part in Ohm's law, and I like to think of Ohm's law as just cause, effect, and then of course there's resistance, which is kind of just an anti-effect. Okay, guys, just editing me, coming back here to mention that current is measured in amps, or amperes, or A. Uh, Also, what that really means is electrons per second. So amperes is just coulombs per second, right? Coulombs per second is amps. Um, and all that really means is how fast the current is going is how, the current speed, but the current itself can be measured in any point on the circuit. Like if you have like a little point in the wire, well, like a cross section of the whole wire, right? And you want to measure how much current is flowing through that whole wire, because that will be the same throughout the entire wire. Then you'll know to use amps, because current is amps. Of course, said you have current like a river. Here's an image of a river. But you don't always have current that flows like a river. Sometimes the electrons stay still. They stay in a battery, stay in a capacitor. They stay in something that keeps charge, And in a bike tire, for example, the air would stay in a bike tire most of the time. Here's a picture of an inner tube. But if you've ever seen a bike tire and used it, you know the bike tire has a valve. Here's a picture, and if you push the valve, you'll release like a slow leak of air, and the pressure of the tire will slowly drop. But if you release the nozzle more, it'll go faster. The air will go out faster. But of course, if you pop the bike tire with like a nail, then take the nail out, the hole is really big, the resistance to the air change is very small, and it will go much faster. It'll deflate your tire within seconds, really. It'll pop your tire. As you can see with the tire analogy, the larger the hole, the faster the air will come out of the tire, and the quicker the pressure drops in the vessel that stores the pressure. Okay. Kirchhoff's current law. So this means that current coming into a circuit, current being the electrons that are coming in, they must be either stored in the circuit, like you could have electrons that go in and they'll have to be stored somewhere, or they could be leaving the circuit, and your voltage is dropping. But the thing is, the current going into the circuit must be the current leaving the circuit, right? Like you're not gonna just like get electrons out of nowhere, and you're also not gonna just lose electrons out of nowhere. And if you are losing electrons in a house circuit, that is, you probably have a ground fault, because the electrons don't just leave without coming back, like unless they leave through ground, usually. Maybe a couple will just like disappear, but if they're not going to get outside the insulators. The lightning. It's the perfect time. Okay. Kirchhoff's voltage law. Voltage applied is divided across all the loads in a series circuit. Meaning you have like one light bulb, and then after the one light bulb, it's another light bulb, and then after that one, it's another one, right? So the current, the electrons, they flow through the first light bulb, then they go to the second, then the third, and then they leave and go back out to the battery, right? They come from the battery and go through the light bulbs, then go back. It So Kirchhoff's voltage law means that in a series circuit, in that light bulb circuit, I'll draw it. Here it is right here. As you can see, the in the one light bulb circuit right here, it's at full brightness with the 3 volts across it. But the other light bulb circuit that I'm displaying under it, you can see it has the 2 light bulbs there, and since we have 3 volts across it, across the 2 light bulbs, it means it divides across the 2 light bulbs, and each light bulb gets 1.5 volts. And the thing about regular incandescent light bulbs is that they get darker the less voltage you apply, because the less voltage you apply means the less current as well. And voltage times current is power. So yeah, that's why if also lights in a lighting circuit are almost always in series. Okay, so important to note, if I have the world's smallest battery and I could fit 2 million electrons into the battery, right? And let's say before I put the 2 million in, it's only at 50% battery charge. But when I put the 2 million electrons in, it charges it 10%, from 50% to 60% battery charge. Then, assuming a perfect world, a perfect system, a perfect circuit, I could extract 2 million electrons, which then would bring that 60% battery, which I just charged, back down to 50%, assuming no loss. 2 million electrons is 1312000000000. That's a big number, but it's really 1 divided by a big number, so it's actually incredibly small per part of 1 coulomb. So 2 million is a tiny, tiny piece of a coulomb, right? A coulomb is huge, but coulomb really isn't that big because the iPhone 14 holds 3,279 milliamps, or 3,279 thousandths. So tiny pieces, right, of 1 amp hour. So that's an amp times an hour, which is 11,804 coulombs of charge, or this enormous number here. That's how many electrons are in an iPhone 14 battery. Okay, it's recording, right? Okay. Okay, guys, so here you see I have my battery packs. I have 2 of them, each with a 1.5 volt battery, all in series. So that's 1.5 volts times 2, which is 3 volts, and then 3 volts times 2 is 6 volts. So here on my multimeter tool, I can read DC voltage. This is DC voltage. What does DC stand for? Direct current. It means it doesn't change. Sorry about the dog. He's scared of the lightning. So if I turn on this by attaching my multimeter pins to the end of my battery, you can see, can you point the camera in on that? Thank you. No, on the screen. Yeah, the actual screen of the thing. Yeah, there you go. Thank you. It says 6.166 volts, so it's a little high of 6 volts. I'm going to use, oh, power is almost low. It's okay. I'm going to use less than that for the LEDs that I'm going to use, and I'm going to use 2 LEDs in series. So the LEDs I need are light emitting diodes. They're just lights, light bulbs. They use 3 volts, and I have 6, so I'm going to put them in series. So, oh, there we go. As you can see, 6.15 volts. But as you can see here, we're measuring across the 2 lights. So we have 6 volts here and 0 volts here. Or you could think of it as maybe 3 volts here and negative 3 volts here.
Yeah, but important to note, this middle point is the middle of these two voltages. So if this is 6 volts, then right here in the middle between this LED and this one should be 3 volts. So if I move this pin, hold on, I'm going to move this here, 3 volts. So as you can see, if I move it back there, 3 volts. Each LED requires 3 volts, meaning we can run the LEDs, 2 LEDs in series on one pack. Let's do that. Okay guys, so you see I have my multimeter and I have my circuit here. I'm going to remove the battery real quick, and I'm going to put it in parallel. As you can see, the current comes out of the negative and goes up and then goes here. Once it goes here, it also goes here. So it goes to these 2 points just the same. It then goes evenly through the, not the resistors, but the load, which has a resistance, and there's a voltage across it, and these 2 lights have the same voltage across them. To prove that, let's test it. All right, Colin, could you zoom in on that 3.094? Really make sure they get it. Hell yeah. All right, so now you see 3 volts is powering 2 batteries. But 3 volts powering 2 batteries means nothing without a resistance value. And the thing about LEDs is that it's hard to get the resistance value. So, yeah. Cut.
Remember that I said current equals pressure over resistance, or the total current measured in amps or amperes equals or is equal to the volts over the ohms, or volts per ohm equals current. This means that we can only choose what voltage we want to apply in a circuit, right? We can also choose what the resistance values for the components are. So like certain light bulbs resist current more than others. And then once we have our voltage applied and our resistance of our circuit, we can then know the current. And then we take our current and multiply it back by the voltage to find our total power in watts. Meaning, volts times amps equals watts. Yes, a new unit, watts. It has direct conversion to heat power, like an air conditioner circuit or a heating circuit. Light power, like in a lighting circuit, like in your house or in a flashlight, or mechanical power, like in motors. It is important to note that all circuits lose power in heat and waste energy. Free watt hours are wasted in heat. This is unavoidable unless the goal of the circuit is to generate heat, like in one of those old school toasters, or one of those the heating things. What are they called? The little metal discs with the heating element that are dangerous. Here, I'll throw up a picture here so you can see.
Ohm's law, it's 2 causes and 1 effect. 1 you can change and 2 determine the rest. Voltage, current, and resistance, you should know the rest. Pressure over ohms, yeah, current is next. Oh,
it's the basic laws of nature. It's by definition electronic nomenclature. Voltage EMF is equivalent to pressure. Resistance drags on and current you can measure. No 2 and 3 and the rest isn't a guess. Ohm's law, yeah, you know it's the best.
direct relationship between three things. Laws of nature, they don't care about your feelings.
Current takes all and every single path.
Kirchhoff.
You don't need a scientist to do the math.
110 volts. Ouch, that stings. 110 volts across your finger. Could it be? Should've listened in J. Debster's 103.
Just make sure so you know how it works. Just make sure so you don't get hurt. Ohm's law, it's a three-way relationship. Pressure, resistance, and the current that follows it. VI or I hope you remember it. Of course, there are many other ways to think of it.
Volts over ohms, current the result. Ever confused, and this formula you'll consider